Marking a take-home quiz. I said that already to you guys, but I got interrupted by students showing up late. I'm a bit of a grumpy bear right now. Here's what I was going to say. On your test, one of the first questions you're going to ask yourself on any of these questions is this point charges or parallel plates? Now, this whole quiz is all point charges, round circular charges, which we refer to as point charges. But I'm going to ask myself that whenever I do these to remind myself that once I have the whole shebang, I'm going to be asking that all the time. So find the magnitude of the electric force between the two charges. You see, it turns out, Emma, there's two ways to find force. There's the charge at that location times the electric field, which is not what I'm going to use here. Or there's Coulomb's law, which is working for point charges. K, Q1, Q2 over R squared. You could also go big Q, little q, but both these charges seem to be planetary, and I'm not in the, okay, whatever. It's going to be 9 times 10 to the 9th, 8 times 10. Mr. Dueck, shouldn't you put negative it? Forces and fields on the first line on your formula sheet. Forget the signs. We're going to decide the direction, although this question only said find the magnitude. Fair enough. Second charge, 4 microcoulombs, all divided by, another late person here. And then, R squared, I think is what we wanted, right? 1.3 plus 0.85, subtract the 3, 2.15, is that right? Yeah. 2.15 squared. Times 8 times 4 divided by 2.15 squared. Any typos? 9 times 10 to the 9th, 8 times 10 to the negative 6, 4 times 10 to the negative 6, 2.5, looks good. Do you get 0.06, I'll go 6.23 times 10 to the negative 2? Is that right? Newtons. Direction, they didn't ask for it. These would be attracted to each other, so I would have to tell you which point I wanted you to tell me the direction on. Q2, the forces to the left. Q1, the forces to the right. I like B, I like B, I like B. B is a nice question. In fact, I'll be honest, I think part A, that's 2 plug and chug. I don't think I ever asked that on the test. I don't think I ever give you 2 charges and say find the force. What I will do is give you the force, give you one of the charges and say find the other charge, or give you the force, give you both of the charges and say how far apart are they? Find R. That's going to be on your test. In other words, as I've said all year, Ryan, if I teach you how to go forwards, as far as I'm concerned, going backwards is always fair game, right? Find the electric field. Well, there's 2 of them. I'm going to find the electric field from charge 1, magnitude and direction. I'm going to find the electric field from charge 2, magnitude and direction, and then I'm going to add them vectorially. Electric field, well, there's several ways to calculate electric field. Electric field is defined as force divided by charge. I'm not going to do that because that would be the charge at that location. There is no charge at that location. Electric field, we learned last day, is change in voltage divided by distance. That's only between parallel plates, and which is why I used the letter D there. Electric field from point charges is K Q1 over R1 squared. It's K Q2 over R2 squared. It's going to be 9 times 10 to the 9th, 8 microcoulombs. Mr. Dueck, shouldn't you put a negative in? Forces and fields, we forget the signs. 1.3 squared. 9 times 10 to the 9th, 8 microcoulombs, 1.3 squared. Do you get 42,600 and blah, 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 blah? 42,604 newtons per coulomb. Direction. Which way would a positive right there want to move if it could because of this guy? To the left, it would be attracted to the left. It's going to be 9 times 10 to the 9th. 4 microcoulombs. 0.85 squared. Thank you, Carly. I wish I'd done that on purpose to make you notice it, but I didn't. That would have been great teaching had I done that on purpose to make you notice it. $49,827. I made these numbers up, so they're not going to work out nice, but they're in the thousands, which we said most electric fields are. 49,827. 49,827 newtons per Coulomb. Which way? Also to the left. So the net electric field, can I fit that in right there? I guess I'm going to add these left plus left, which is not going to be winner minus loser, Rachel. It's going to be winner plus winner. It's going to be this plus 42604. And now I'll go to 3 sig figs. 9.24 times 10 to the 4th. 9.24 times 10 to the 4th newtons per Coulomb left. If you got that, 2 out of 2. Otherwise, I would give you half mark for that, half mark for that, half mark for that, and a half mark for the direction. Okay. Hayden, my friend. Hayden. Wow. Hayden, my friend. Yeah, I'm waking up. I got that. Yeah, hey, it's been a long weekend for me too. Anyways. What is? Can you read C to me? Okay, electric. Oh, potential. So I guess they want me to go K Q1 Q2 over R. No, because what's that? That's not potential. It's potential energy. I guess to find at location A, oh, and also at location A, there is no point there for. Yeah, there's 2 points in the picture. Oh, I like example. I like this question. I like this question. I like this question. I think then what they want me to do. What's another word for potential? Voltage. I'm going to find the voltage from charge 1. I'm going to find the voltage from charge 2, and then I'll add them up vectorially. No, scalar. And each of these is going to be K, Q over R. It's going to be 9 times 10 to the 9th. Negative, because we're in scalarville. All over 1.3, which is, you know what, with a bit of cleverness, I think I can bring this up. I think I just got to insert a negative right there and delete the squared right there. And negative 55,385 volts. On the right-hand side, we have 9 times 10 to the 9th. Positive for, you can switch back now, Michael, all over 0.85. Yeah, I made it fairly difficult to do. That was, you know. 9, oh, wait a minute, Mr. Dueck. Let's be clever. Bring back the same thing here. Delete the negative, put a 4 there. 0.85, that's less typing. 42,353. 43, Mr. Dueck. 42353. Add them up. The voltage is going to be that plus negative 55,385. Looks like the voltage there is negative 13,000 volts. Okay. What does that mean? It means that if you started out with a positive charge right there, you would have to add energy to move it out to infinity in any direction. Because there's a negative voltage. That means every single Coulomb of charge has negative 13,000 joules of energy. 2 marks if you got that. Otherwise, I'd probably go something like this. Half mark for that. Half mark for that. 1 mark for adding them up. Turn the page. Hey, this wants to know how much work. Well, that's going to be change in potential plus change in kinetic. I don't see any speeds mentioned, so I think I can safely do that. It's going to be, do I know the voltage at all? No, because if I knew the voltage, the change in voltage, then I could just go Q change in voltage, which was really a lovely, lovely shortcut. They didn't tell me that, so I think it's going to be, Holly, final minus initial. Oh, wait. Right? My initial is infinity, which is 0. So this isn't as much, no pun intended, work as I thought it was going to be. It's just going to be K, Q1, Q2 over R final. The amount of work is going to be 9 times 10 to the 9th. Negative work, scalar, energy, scalar, negative 6 microcoulombs, charge 2. It's an electron. Help me out. Not 1.6. Negative 1.6 times 10 to the negative 19. All over 0.12. 9 times 10 to the 9th, negative 6 microcoulombs, negative 1.6 times 10 to the negative 19, divided by 0.12. Do you get 7.2 times 10 to the negative 14 joules? Wow, something worked out fairly even for a change. You get a positive or a negative answer. You get a positive answer. You know what? I'd probably, for part marks, go something like this. 1 mark if I saw that line. 1 mark if I saw KQ1, Q2 over R final. 1 mark for the numbers and 1 mark for the answer. The fact that it's positive, here's what it's saying. The electron does not want to move closer to this negative charge. That's why I made that first charge negative. I wanted a positive answer. You would have to, Holly, be pushing it the entire time, and it would get harder and harder to push the closer you got to this negative charge, because it would be repelled more and more and more and more and more. You would be adding energy. You would be doing work. Now, if this question instead had said we are moving a proton, you would actually get a negative answer. What it would be telling you is, actually, you don't have to do any work. Negative work, you would get some energy back that you use for other stuff. It would want to move that way. I think I did something kind of like that. Yeah. I set up a situation where the charge wanted to move away in number 3. Number 3. Scalar, not velocity, scalar. I think to myself, there's a change in the height if I imagine height as sideways. There's a change in speed, scalar, probably a job for conservation of energy. It says initially at rest. And I'm pretty sure the speed is going to end up there, so I'm going to minus PE final over. I'm going to go PEI minus PEF, that equals a half mv final squared. I'm not going to get the v by itself. I'm going to crunch the numbers. This is going to be K Q1 Q2 over R initial minus K Q1 Q2 over R final. That equals a half mv final squared. How much room do I have? Write small, Mr. Dueck. K. Probably going to need that right-hand side. 9 times 10 to the 9th. Charge 1, 6 point positive, 6.5 microcoulombs. Charge 2, it's a proton. 1.6 times 10 to the negative 19, all over our initial 1.2 plus ditto mark, ditto mark, ditto mark. We don't need a bit more room. All over our final, not 2.2, common mistake. Our final is that whole distance, which is 3.4. Oh, is a minus in between them? There you go. You're right. I was doing the minus. Minus becomes a plus thing from work at energy. This is not from gravitation. This is not that. Stuff can fall up here. Equals a half mv final squared. I should have left more room. Oh well, let's see what we can do here. 9 times 10 to the 9th times 6.5 microcoulombs times 1 proton divided by 7.8 times 10 to the negative 15 minus 2.754 times 10 to the negative 15. That equals a half mv final squared. Let's actually crunch the numbers. 7.8 times 10 to the negative 15. Careful, Mr. Dueck. Times 10 to the negative 15 minus answer button. Thank you. That would have screwed everything up. Is that how much energy we have? I think so. 5.047 times 10 to the negative 5.005. 5.047 times 10 to the negative 15. That equals a half mv squared. Now let's get the v by itself. V is going to be 5.04. You know what? I'm going to times by 2. Let's put the 2 in front. Times by 2. Divide by m. Huh? It's a proton. I know the mass is 1.67, but I can never remember the times 10 to the. That's v squared. How to get rid of a squared? Square root. So it's going to be 2 times this divided by 1.67 times 10 to the negative 27. Whew, square root. Do you get 2.56 times 10 to the 1, 2, 3, 4, 5, 6? 2.56? 2.46, Mr. Dueck. 2.46. Is that right? People nodding? How would you get part marks out there? Well, I give you full marks if you got the right answer. Otherwise, I'd probably go something like this. Half mark for this line, 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 half mark here, half mark here, half mark here. Please tell me that 7 halves. 1, 2, 3, 4, 5, 6, 7. Yep. And a half mark for the answer. Probably something like that. Whew! That was good, Mr. Dueck. Point charges, all the stuff we can do. I forgot to put what this thing is out of. 2, 4, 6, 10. I guess this quiz is out of, count 'em, 14. If you could put a score there out of 14, that would be much appreciated. Lesson 7, parallel plate force problems. Next lesson is going to be parallel plate energy problems. And then lesson 9 is going to be a review of everything, because after I've showed you everything is when all those equations start to look alike. I'm going to try and give you dumb ways to keep track of, hey, which equation do I use when? Because they all have a K, and most of them have a Q, and most of them have an R, and some have a squared, and some have another Q, and some don't have a square. Like, okay. Recall from last lesson, we said if you take parallel plates, metal plates, and you hook one side up to the positive part of a battery, and you hook the other side up either to the ground if you want a 0 voltage, or you can hook up the negative part of the battery and even increase your voltage. We said this, the electric field was the change in voltage divided by the distance. We also said the electric field in between those plates was constant. And that, McKinley, you were away, but that gave us some very nice math. It's going to give us some much cleaner mathematics. Okay? So keep that in mind, that we can generate any electric field we want to by bumping up the voltage or by moving the plates closer together. Example 1 says this. Explain why an atom will be ionized. You guys are in grade 12. Ionized means that the electron has been separated from the atom. That's why we call it ions on your periodic table, all those charges that you learn. If it's placed in a sufficiently large electric field, you can create ions by putting atoms in a sufficiently large electric field. You can rip the electrons off. Why? Well, first of all, what direction is this electric field in my picture? To the left or to the right? Sorry? To the right, which means which way would a positive want to move if it could? What direction is the electric field here? To the? Which means which way would a positive charge want to move if it could? To the right. Now, where are the positive charges in an atom? You guys know your basic chemistry. Okay, in the nucleus, and they're really locked in there with the strong and weak nuclear forces. What charges are free to move in atoms very easily? Electrons. So if the electric field is pointing to the right, which way would an electron experience a force? To the left. Okay, you follow that reasoning? If a positive would move to the right. So if you have an electron right here, it will experience a force to the left. It says, why will an atom be ionized? Electrons are negative, and more importantly, they're also free to move. Electrons are very easy to move. You can move them around by, again, you do this in Science 9. You take a plastic ruler stick or a plastic stick, you rub it with a cloth. Holy smokes, you've charged it that quickly. Now, electrons move very easily through conductors, but we want to talk about specifically, instead of ionizing or moving through metal wires, we want to talk about how you ionize air. Because this, Jake, is how we're going to talk about what happens when you get a shock. I don't know if you've ever gotten a shock from a metal object on a dry day. You don't get the shock when you touch it. You may think you do. You get the shock actually when you're very, 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 very close to the object. In fact, you get the shock when you lower the distance enough for the voltage to have a sufficient electric field to ionize the air. To ionize the air. So if we're talking about air, which is mostly nitrogen and oxygen, we have done studies. It takes around 3 million volts per meter to produce ionization. And this may seem like a very, very big a number, but actually 3 million volts per meter happens an awful lot. It's the crackle that you hear when you pull apart clothing on a dry, staticky day when you're taking it out of the dryer. It's the shock that you get when you walk across a carpet on a cold winter day and then reach for a doorknob. It's lightning. So, how can we increase the chance of a shock occurring? We need to somehow get the electric field up to 3 million. Well, there's two ways, Grant. You can make V bigger, or you can make D smaller. Put your pencils down, look at it. So, Each of these effects is accompanied by light. The light occurs because the ionized electron does not remain free. It quickly falls into the orbit or the shell of a neighboring atom, and it's got some extra energy. The energy's got to go somewhere, gives off a photon of light. That's why there's a spark when you shock something. Well, big deal. Actually, no. We can treat a cloud as though it's a parallel plate. Thunderheads are roughly flat on the bottom. So the bottom of a cloud is charged to 2.5 times 10 to the 8th volts from cosmic rays that pass through the atmosphere. How close would this cloud need to be to the ground for a lightning bolt to occur, keeping in mind that the air breaks down at 3 million volts per meter? So this is a parallel plate. This is positive. This is negative. We know that for parallel plates, electric field is given by the voltage divided by how far apart the plates are. Ty, what does this question want me to find? Electric field, voltage, or distance? Distance. Let's get the d by itself. Oh, you know what? This is technically 1 fraction equals 1 fraction. Stuff moves diagonally. I would times the d to this side, divide the electric field over to this side. Turns out, if you want to know for this particular situation, it's going to be the voltage divided by the electric field. What's the voltage? 2.5 times 10 to the 8th. What's the electric field required for air to ionize? Around 3 million. Or 3 times 10 to the 6th. By the way, that varies. It depends on humidity. It depends on a number of other factors, so this is very rough. How close would this cloud need to be for lightning to occur? $83.3 meters. Not that far, fairly close. This also explains something else. Where would you not want to be in a lightning storm? Why is standing under a tree a bad idea? What does the tree do in terms of the physics? It reduces the distance. Yeah, reduces the distance required for that shock to occur. So this would be a bad place to stand. Oh, I guess that would also be a bad place. Top of a mountain, you've just reduced the distance. Every year, hikers that are hiking in mountains get hit by lightning. If you are ever hiking somewhere in the mountains and you feel that staticky feeling on your skin, you feel your hair standing on end, get out of there. And I mean get out of there within 5 seconds. Tell everybody, start hustling, start jogging down to a lower altitude. Okay? Because often in mountains, you're screened from the weather. The thundercloud might be on the other side of the mountain. It might be screened out of your view. Boats are bad for 2 reasons. First of all, water is a good conductor, and so lightning could hit the water and easily conduct it to the boat. But also, there's a very specific type of a boat that essentially has a metal lightning rod built in. Okay, so this would also be a bad area to be. What should you do if you're stuck in a lightning storm? Crouch down. The other thing you want to do is you want to keep your feet as close together as possible. If you are standing, I'll draw you like a boxy person just to keep this as simple as possible in terms of the physics, okay? If you have one leg here and one leg here, those 2 legs have just become parallel plates. Okay? And lightning can go up one leg and either cross through your heart or it can arc between your legs. In fact, cows are notorious for not being able to survive lightning strikes very well. Why? Well, because a cow, if we look at a side view, again, I'm going to do a boxy picture. A cow has one set of legs right there, one set of legs right there, and you're almost always then going to have a change in voltage between them as the charges travel this way. They've set up a little parallel plate system. This is not good. That's why they say keep your feet together, preferably touching. Shuffle if you're stuck in a lightning storm. Or if there's a down power line, you've heard the radio commercials, shuffle your feet away. Now, if you know the field, we can find the electric force by going oh, but Atla, I've just told you that between plates, the electric field is the change in voltage divided by how far apart they are. So I guess we can combine these two. This is not on your formula sheet, but you want to find the force on a charge between plates. It's going to be Q voltage, change in voltage technically, divided by how far apart the plates are. Now, who remembers what that was? It's sort of on your formula sheet. It's potential, Jake, what? It's potential energy. It's potential energy. If you times the d over to this side, you'll suddenly see, because we have a constant force, force times distance does give you energy once again. And we've avoided that for the longest time, both in gravity and in electrostatics as our force was changing. But I said to you, McKinley, the math gets much nicer between plates because of this constant electric field. Oh, it's a scalar equation. We figure the direction of the force by cluing in, hey, which side of the plate is positive, which side of the plate is negative, like repel, unlike attract, depending on how big the charge is between the plates. Turn the page. In a very, very famous, example 4, got to do that first. Find the acceleration of an electron placed between metal plates that are separated by that and charged to 275 volts. Okay. What's this question want me to find? Haven't done that for a while. It's like physics 11. Well, we always said there's two ways to find accelerations. There was kinematics, Vf equals Vi plus AT equals Vit plus a half AT squared, Vf squared equals Vi squared plus 2AD. And there was also forces, because F equals Ma. I think I'm going to start there, Holly, what with the fact that we just wrote a force equation. We just said this. The force between parallel plate, well, the force on a charge is in an electric field is QE. Again, Emma, important, this equation not blatantly on your formula sheet, but this one is, because that's how we defined electric field, so it's a rewrite. F equals Ma, that equals Q. Oh, and what did we say the electric field between plates was? And the reason I can use this is because the force is constant. If the force wasn't constant, I'd actually have a changing acceleration, which I think I'd need calculus to handle. Because acceleration is a rate of change, and I'd have a rate of change that had a rate of change. It'd be the derivative of acceleration. I think it'd be a jerk. What's this question asked me to find? Oh, get the A by itself. You know, this looked ugly at first, but actually this is fairly plug-and-chuggish, Rachel. I'm going to divide by M. So I'm going to get this. The acceleration is going to be Q, the voltage that it's traveling through, the change in voltage, divided by MD. Q, it's an electron. Okay. By the way, which way would this electron want to move in that picture, up or down? Up or down? Why up? You're right. Because electrons want to move from what to what? From negative to positive. Which way is the electric field? Down. Why? Because electric field is defined as which way would a positive want to move it could. Okay. What's the change in voltage? What's the mass? Oh, it's an electron. I know electron is 9.11, but I can never remember the 10 to the. And the distance, don't say 2.5 meters, 0.025. Now, look up. Although I said for scalars, we put in the charge, we're finding acceleration, which is technically a vector, so we don't put the negative. We're just good with the 1.6. Because this is a vector equation. I should have corrected that. You're going to get a huge acceleration, like really big. Well, you don't notice it when electrons move. Your eyes can't follow it, so it should be a fairly big acceleration. Not instant, but close. 1.6. You get 1.93 times 10 to the 15th meters per second squared. Yep. Up, if they'd asked for a direction, they didn't specify. This is terrifyingly large because the speed of light, which is the cosmic speed limit, is only 3 times 10 to the 8th. And you're saying that this is accelerating at basically 2 times 10 to the 15th. That means in 1 second, this will be going almost twice the speed of light. Have we violated the laws of physics? No, because it's not going to be traveling for 1 second. In fact, now that you know the acceleration, VI is 0, you could actually find the time to travel 2.5 centimeters, and then you could actually calculate VF, and we're not breaking Einstein's laws. It won't have a chance to get that fast before it runs out of voltage to travel through. Really won't, so we're okay. In a very, very famous experiment to measure the charge on an electron, Millikan used parallel metal plates to hold in place a charged oil drop. He had gravity pulling it down. He knew the mass. He had electric force pushing it up. And because he had an equilibrium situation, he said, I can finally solve for Q. This is how they found, because by the way, the charge on an electron or a proton, 1.6 times 10 to negative 19, that's really small. That's even smaller than big G, and I went on a big song and dance about Cavendish's clever experiment to calculate the 6.67 times 10 to negative 11. So, the charged oil drop below is at rest due to gravity and electrical forces. First question, what's the sign, what's the polarity of the charge on that oil drop? Does that charge, for it to be hovering there, have to be charged negatively or positively? Well, what direction is the electric field between those plates, up or down? Down. Down. What are the forces acting on this? Get the obvious one. Gravity, absolutely. Now, if it was positively charged and the electric field was pointing down, which way would a positive charge want to move if it could? Also down. You know what? This has to be charged negatively because that way we get electric force pointing up. We can suspend it. We can suspend it. In fact, B says, write a balanced force equation. You know what? I think gravity equals QE equals FE, but I even went further. I said I know electric force is QE. In fact, I really could have gone like this. Gravity equals Q, change in voltage, divided by the distance. This was a nice setup because even 100 years ago, even longer than that, we already had reached the point where we could, using dials and knobs, tune the voltage very accurately. So we could literally turn a knob, it's going to fall, turn it up, oh, now it's moving up, turn it there. Okay, what voltage? Okay, I got that voltage, measure the distance, we could keep it hovered there. So let's try it. Example 6, a particle of that mass, and we know it has a charge of -3 electrons, is suspended between parallel plates. What's the voltage on the upper plate in order to keep the charge in equilibrium? Okay. What are the forces acting on this charge? Gravity down. Has to be same size electric force up, because it says it's in equilibrium. I guess there is no part A. So my equation is this. Gravity equals electric force. Gravity equals QE, which is also electric force. Gravity equals Q, change in voltage, divided by distance. What's this question want me to find? Oh, let's get the V by itself. Divide by Q times by D. The voltage required here would be mg times by D divided by the voltage. No, not divide by the voltage, divide by Q. Voltage is what I'm trying to find, Mr. Dueck. Sheesh. Let's see, hopefully they've told me everything that I need. Mass, 2.3 times 10 to negative 14. G, 9.8. D, 0.015. And they told me the charge was -3 electrons. I'm going to ignore the negative just because I know that top voltage must be positive since 0 is at the bottom and I want an electron to move up. So I'm just going to, I know what my result should be. 3, 1.6 times 10 to the negative 19s, 3 electrons. About 7,040 volts. And we can do that easily. In fact, we can generate hundreds of thousands of volts. Homework to try. Number 1. Number 2. Number 3. So number 3, here I'm telling you the acceleration, and I'm saying find the voltage. So number 3 is this question here, kind of done in reverse. I'm giving you A. I think you can work your way back and figure out what the voltage has to be. 4 is good. 5 is good. You want 6? Okay, I'm good for 6. Find the field force electron. Number 8. Yeah, 9 is good. In fact, sorry, but I like number 8 and I like number 9. I like number 8 and I like number 9. Field force, acceleration, final speed. Field force, acceleration, final speed, yeah. Sure, 10. We'll pause there. So, lightning. Let's talk about it.